In this video, I'm going to analyze the behavior of blackbody radiation at different temperature via experimental data. To this end, let us begin by analyzing the behavior of radiation emitted from the opening of a heated blackbody radiation at different temperature. If the emissive power for different wavelengths are experimentally measured and plotted against the emitted wavelengths, continuous curves ranging from infrared to ultraviolet regimes and bearing a very special behavior are obtained. That is, unlike the emission spectrum of gases which are discrete in nature, the emission spectrum of blackbody radiation is continuous. To conceptually understand the special feature of these curves, I want to plot them for 4 different temperatures, starting from a relatively lower one and moving on to relatively higher ones. Let us take the wavelength lambda along the horizontal and the emissive power along the vertical axis. For a relative lower temperature, which I denote by T1, the curve remains closer to the horizontal axis, such as the one shown in the figure. One can see that the curve has a maximum at a particular wavelength, which I am denoting here by lambda sub max, and it represents the maximum emissive power at temperature T1, which here I am representing by R sub lambda sub max, because the emissive power for all the rest of the wavelength is lesser than this one wavelength. The total emissive power of blackbody at this temperature between the two end wavelengths lambda 1 and lambda 2 is equal to the area enclosed by the curve with the horizontal axis. Increasing the temperature and repeating the same procedure, a curve with larger enclosed area with the horizontal axis is obtained, such as the one drawn at temperature T2. We see that this curve encloses larger area with the horizontal axis, which means that the total emissive power in this case is larger than in the case of temperature T1. So increasing the temperature of a blackbody in fact increases the total emissive power. Also note that the limits of the wavelengths at the two ends of the curve has also been extended. The wavelength at which the maximum of the curve occurs has also shifted to the region of lower wavelength, and the amount of emission power has shifted to larger value. Note also that the emissive power corresponding to the wavelength at which the maximum at temperature T1 occurred has also shifted to the region of larger emissive power. In short, at higher temperature, the emissive power corresponding to every wavelength has increased as compared to the case of temperature T1. If we keep on increasing the temperature and plot the emissive power against every wavelength, the same behavior is repeated for every larger temperature. That is, the area enclosed by the curve at higher temperature along the horizontal axis or wavelength axis increases, and the maximum of each curve at higher temperature shifts toward the region of lower wavelength, and the emissive power for each single wavelength increases as compared to the emissive power at lower temperature. You can observe this very easily for the curves plot for temperature T sub 3 and temperature T sub 4. This was just a short review of what was observed from the experimental data on blackbody radiation. In the next video in this playlist, I'll be reviewing the empirical formulas and the theoretical formulas derived for explaining this behavior of blackbody radiation. So stay with me and wait for the next video.